Okay, we skipped lesson 84. Looked at it, didn't like it, didn't see a whole lot of point in it as far as what we're doing. So we're going to skip ahead to lesson 85. And the name of that lesson is Systems of Nonlinear Equations. Well, at this point, we've been dealing with linear equations, like y equals 2x minus 4. And one of the things that we've said about linear equations is that when we graph them, we get a straight line. And one of the ways we can look at this equation and know that we're going to get a straight line is we do not have an exponent here, and we do not have an exponent there. So that gives us our straight line. We're able to solve it. Life is good. Well, in this section, nonlinear equations, we're going to get into some different things other than straight lines. The most important nonlinear figures are called conic sections. And let me show you in the book, page 350, if you want to turn there, but there's the page right there. These are conic cones right here, and these gray planes there are called conic sections. And what happens is we can cut this, or I'm sorry, they're just called planes. What the plane cuts is called the conic section. So this area right here is a conic section. When that plane cuts parallel to the base, see how it's straight across? We get a circle. When we take that plane and we cut it at a kind of an angle here, in fact it doesn't even matter what angle, what we get is, if we were to take this top part off and throw it away, we'd be left with this picture right there cut away. Okay, so that's at an angle. And then this one here, if we take a plane and don't go all the way across this line and this line, we just kind of take it and angle it down this way, we get a parabola. And then notice here with this conic section, or this cone here, we've got a cone and then we have another inverted one, so they're kind of point to point. And if we were to take a horizontal plane and cut through here, see how it leaves this area right here and this area right here exposed, or this here, which is called a hyperbola. So we'll get into all of these later. I mean, there's the formulas for those, but we won't worry about them at this point. But to solve a system, let's get back to my paper here. Whoa. Alright, let's call that good. Okay. We have a system that we're trying to solve, and let's say that this particular system is x squared plus y squared equals 9, and then 2x minus y equals 3. Okay, so this is system of equations, which we've done before. Let's kind of move this over a little bit, see if I can get it to show up better. Alright, so normally what you would do is, most of you are used to using elimination, where you multiply the top number by what you need here. So like in this case, you'd multiply the top number by 2 or negative 2 to get the x's the same, so you can subtract them or add them and get them to be 0, and then you solve for y, etc. But these exponents up here cause you a great deal of grief, so you can't use elimination. So we're stuck with substitution here. So what we're going to do is we are going to solve for y here. So we end up with y equals 2x minus 3. So now, whenever we see that we have a y in this top equation right here, we're going to substitute 2x minus 3 into that equation. So let's do that. X squared plus, now instead of y squared, we're going to put 2x minus 3. We're going to square it, and that's going to give us 9. So we use the FOIL method and square that. We get x squared plus 2x times 2x. Our first term is 4x squared. And then our middle terms are going to end up adding together and give us negative 12x plus 3 times 3 is 9 equals 9. Then we can combine our like terms here and get 5x squared minus 12x equals 0. And then we factor out an x. And now we have two values of x. X is going to equal, what's going to make, when I multiply this whole thing together, what's going to make it 0? Well, if x is 0, 0 times whatever this is going to give me 0. Or x is going to be whatever 5x minus 12, whatever makes that 0. So I got to figure out what's going to make this whole thing here 0. So 5x equals 12, and divide by 5, so 12 over x is going to make that 0. So 12 over x. So there are two solutions to this problem, and if you remember right, when you have an exponent of 2, clear back up here in the original, that tells you how many x values you're going to have. Okay? So, in order to find y, we're going to take our original equation. In fact, in this case, let's use this equation right there. We're going to plug our x values in and see what our y is going to be. So, let's write it down here a little bit. 2x minus y equals 3, and we said that our x value was 0, 12 over x, that's 12 over 5, isn't it? I'm sorry. We're going to plug in a 0 for x, so 2 times 0 minus y equals 3, so negative y equals 3, or y equals negative 3. Okay, so when x is 0, y is negative 3. Okay, we do the same thing for 12 over 5. We have 2x minus y equals 3. And now we're going to put 12 over 5 in there wherever we see an x value. Okay, got that. Then we can subtract y, and that equals 3. So 24 over 5 minus y equals 3. And we subtract 24 over 5 from both sides, and we get negative y equals 3 minus 24 over 5. Find common denominators here. So negative y equals, we'll use a 5 down there. So if we make this over 5, we have to put a 15 up here. So 15 over 5 is 3. So we just change what it looked like. Minus 24 over 5. And 15 minus 24 is at negative 9 over 5, and that equals negative y. And because I have a negative here and a negative here, I could just make them positive. Okay, so I ended up with two different values here. I ended up with, when x is 0, y is negative 3 from up here. When x is 12 over 5, like we had up here, y is equal to 9 over 5. Okay, continuing with lesson 85, I'm looking at an example on page 352, example 85.2. You've seen things like this before. It's called systems of equations. We just did one, but one of the nice things about this one is that there are no exponents. So, naturally, in your intelligent brains, you figured out that because there is no exponent, because I just said a few minutes ago, you can either use elimination or substitution, because you couldn't use elimination on the last one because you had exponents. This one doesn't. But one of the things that it does have is a bunch of weird letters on here, and I just want to do these because it gets you used to all of this, all of the different letters. Again, all these letters do is stand for numbers that we just don't know what they are yet. Okay, so we've got a B here and a T here. These are two different letters representing two different numbers, and it says that because there's no sign, there's no plus, minus, division, or multiplication sign, whenever you have two letters together like X, Y, that means multiply. It's the same thing with this BT here. Okay, this D here is a subscript because it's just telling you a little more information about what this time is. So for instance, let's say that this was the time that you took your boat down the river, okay, compared to going up the river. You want to represent both going down the river and up the river in time, but how do you keep yourself organized so that you know when you're talking about going down the river or going up? So you use T for both of them, but you may use the subscript D for going down the river, and you may use a T to the U power to mean the time to go up the river. So that's the reason for the subscripts. They don't really mean anything except to give you a little bit more information about the time, or whatever other thing you're looking for. I mean, if you were using rate, you may say, how fast was I going up the river? So you might write it as RU, and down the river you might write it as your speed or your rate down the river. So anyway, just a little bit of information about what that is. Okay, so if you look at this, and you're allowed to use elimination here, one of the things that you'll notice is your TD and TD both have the same coefficient in front. This one even has a minus to help you out. So when you add these together, you end up getting 2B, T, D, these cancel out and give you 0, equals 40. Then we divide, and your B, T, D equals 20. Okay, all seems really nice and simple, but the problem is BT represents two different numbers, two variables. It's like saying XY equals 20. That doesn't really help you a whole lot. You want to know what X is and you want to know what Y is, not what you get when you multiply them together. So I'm trying to find out what my BT, or what my B is and what my T is. So one of the things that I do know is that my B times T is 20. So actually, if I went back up here and replaced that whole kit and caboodle there with 20, I could then find out what TD is. So that would be a good thing. So let's put 20 in for my B, BTD. I'm trying to get the light right and everything. It's kind of hard to do that. Okay, so 20 plus 5TD equals 25. Okay, so bring my 20 to the other side, and I have 5TD equals 5. Divide both sides by 5, and I find out that my TD equals 1. Okay, that's kind of nice. Out of my BT, and I know that BTD equals 20, and I know that this is 1, that means my B has to be 20, because 20 times 1 gives me 20. So I just found both my variables there, my B and my T, and then I knew from way up here that when I multiplied them I'd get 20. Okay, so this section is important, just doing the systems of equations with some of these weird variables, just to get you used to doing some like this. The practice, there's one like that, and you look on page 353, their number 6 is like that, but they're really not too terribly difficult, and I think you'll be fine with them. So Anyway, have fun, guys.